Okay, this is chapter 7.2, measuring the quality of a survey. We're going to use a simulation to develop an understanding of the behavior of estimators. We're going to consider the 8 students in a classroom to be the population, so we're going to deal with a really small population again. The students in this classroom consider themselves to be either cat people or dog people. The following lists the students and their ID numbers, and to keep things simple, the students are not listed by name, but by their cat and dog status. So we've got 8 people here, and 8 ID numbers, 8 responses. So what is the proportion of cat people in this population? See that the first 2 are cat people out of a total of 8. So 25% identify as cat people. What symbol do we use to represent this parameter? Because it's a population, we're going to use P. And in this case, again, P is 25%. And so now, number 2, we're going to take a random sample of size 4 from this population. Following is a copy of a portion of the random number table from the back of your textbooks. I randomly selected the first block in line 6 to start. And closing your eyes, putting your finger down, opening them up. This is where my finger landed, right there. All right, so reading from the left, I'm going to select the following ID numbers and students. And I'm going to skip ID number 9 because there was no student with this ID number. Or we had the ID numbers 1 through 8. So we've got 8, first ID number, and then 7964 appearing in this table. If we glance back up, go up there just for a brief moment, we'll find that these ID numbers correspond to dog people. So we've got 8, 7, oops, and 6 and 4. And so that's where this bottom row of the table came from. Again, ID number 8 was a dog person, person with ID number 7 was a dog person, and so on. All right, so what proportion of cat people in this, or what is the proportion of cat people in this sample? We didn't get any, so we had 0 out of 4, or 0%. And what symbol do we use to represent the statistic? It's a p hat, because it's a statistic. It's a proportion from the sample, or the proportion of the sample that are cat people. So we've got 0% in this case. And number 3, we're going to do this again. So we're going to take another random sample of size 4 from this population. I randomly selected the third block in line 1 to start. I went to line 1. Here's where my finger landed. Okay, so if reading from the left, I'm going to select the following ID numbers and students. Again, we're going to skip a couple of these. We're going to skip 9 and 0 because we didn't have anybody with those ID numbers. And let's see, we've got 1 is the first ID number, 3, 5. We got to skip 9 again, another 0, and then 6 is our last ID number that we selected. All right, so again, glancing back to previous page, you can verify that ID number 1 was a cat person, and the other 3 ID numbers corresponded to dog people. All right, so now we have enough information to answer the following questions. So what's the proportion of cat people in this sample? We had 1 out of 4, or 25%, that identified as being a cat person. And the symbol that we use to represent the statistic is again a p hat, because it's the proportion of the sample that had this characteristic. Right, so one more time, number 4, let's take one more sample, random sample of size 4 from this population. It's the last one. I randomly selected the first block in line 1 to get started. So my finger ended up there when I closed my eyes and put my finger down. So ID number 2 was the first person selected. I've got 1, can't use 0, didn't have an ID number 0. And then I got 3, oops, 1, 3, and 3. So notice I'm doing this with replacement. I got the person with ID number 3 selected a second time. All right, so reading from left to right, again, those are my ID numbers. And glancing back, I can verify that ID numbers 1 and 2 were cat people, and ID number 3 was a dog person. So again, this was with replacement. What proportion of the cat people, what is the proportion of cat people in the sample? It's 2 out of the 4, or 50%. And the symbol we use to represent the statistic is again p hat, because it's the proportion of the sample. In this case, or in this sample, p hat is 50%. And so let's take a closer look at our results so far. So we've got 3 repetitions. We took 3 samples in our simulation. Each time the population parameter was 25% cat people. We're dealing with the same population each time. But notice in this column are sample statistics. So this is the result of each sample. These changed. We had 0% CAT people the first time. We had 25% CAT people in our second sample and 50% in our third sample. Notice that 0% is the same as 0 people. 25% was the 1 out of the 4, and 50% was 2 out of 4. And so observations, and keep in mind that the population proportion, which is P, never changed. It was always the same percentage, 25% of the population each time were CAT people. Sample proportion P hat, though, did change. It can change from sample to sample, or it varies from sample to sample. This is because P hat depends on a random sample. In this simulation, we collected 3 samples and counted the number of CAT people. And so I'm going to start over with number 6 again. I lost my earpiece for a moment there. All right, so number 6, in the simulation, we collected 3 samples and counted the number of CAT people in each sample. We're going to complete the following approximated probability distribution from our class simulation. And it's approximated because it comes from a simulation. So if we look back up at our results, let's go up just a little bit. Our estimated probability of getting an outcome with 0 CAT people, notice that happened once out of 3 times. So our estimated probability is about 0.33 or 33%. And we had 1 sample out of 3 where we got 1 CAT person. So again, our estimated probability is 0.33. And same thing for 2 CAT people. That happened once out of 3 times, or 1 out of 3 samples. So that was also an estimated probability of 0.33. And our probability distribution over here looks like this. So we're just extending the line above 0, 1, and 2 up to 0.33 on the vertical axis. And those should be the same height. You can probably do a better job on your paper than I'm doing on the board here. And so notice on our horizontal axis, this is the number of CAT people. And over here on our vertical axis, it's giving us the probability, estimated probability that each of these outcomes will occur. And so number 7, we can also consider the P hat, the sample proportion, to be our outcome of interest. Because P hat is random, it also has a probability distribution, which in this case is called a sampling distribution. It's called a sampling distribution because P hat is a statistic from a sample, and it is used to estimate a population parameter. Let's create the approximated sampling distribution based on the results of our class simulation. So notice in this case, our horizontal axis is a sample proportion. So these are P hats. Vertical axis is the same though, it's probability. Right, so in this case, we want to know what is our estimated probability that we get 0% or 0 CAT people. So we know that that was 33% from our simulation. So what's the probability that we get 25% CAT people? Remember, 25% is the same as 1 CAT person. So that also had an estimated probability of 33%. And 50% CAT people is the same as saying, what about 2 CAT people? Well, our estimated probability for that was also 33%. So these 2 graphs look alike. The only difference is how we labeled the horizontal axes. And up here it was the number of CAT people, and in our sampling distribution, we're interested in the sample result, the proportion itself. All right, number 8, what does the exact sampling distribution look like? Well, there are only 3 possible outcomes or values of P hat in the sampling distribution. You can get P hat equal to 0%, which meant that 0 out of the 4 students are CAT people. You can get a P hat equal to 25%, which indicates that 1 CAT person out of 4 students was in your sample, or P hat of 50%, which means you got both CAT people, 2 CAT people out of your 4 students. So the probability of each of these outcomes can be determined by looking at the sample space for this random experiment. Turns out that there are only 70 possible outcomes, or 70 possible samples of size 4. So rather than listing these outcomes here, we'll focus on how often each outcome occurs. So the probability of obtaining each P hat is shown in the following probability table, and also in the following sampling distribution for P hat. So notice we've got our 3 outcomes that are possible here. Again, 1 CAT person, 2 CAT people, oops, and that's actually a mistake. It should be 0 CAT people, 0 out of the 4, 1 cat person, or 2 cat people. Okay. And this counts here how many of those 70 outcomes or how many of those 70 samples had each of those possibilities. So 0 cat people, that happens in 15 out of the 70 outcomes. 1 cat person, 40 of the 70 outcomes had that result. And 15 out of the 70 outcomes had 2 cat people. So these have been converted to percentages. So we're going to take this one as an example. This should give us the height of this first line segment above 0%. So getting 0% or 0 cat people happen about 21% of the time in that sample space. 1 cat person, and that's right here, 25% of the sample, or p-hat of 25%. This had a probability of about 0.57. And then 2 cat people, looks like that also, same height. So we've again got about 21% of the sample results had 2 cat people, or p-hat of 25%. Right, so a couple of observations. The mean of this distribution is 25%, or p equal to 25%. That's right in the center of the distribution. Our estimator p-hat isn't always equal to p. Remember that p was 25% because 2 out of the 8 people in the population said they were cat people. And so this is a big deal. Your estimator, your sample result p-hat, is not always going to be the same. It's not always going to be equal to the population proportion. So keep in mind that statistics that come from random samples are also therefore random. This means that we cannot know what estimate our sample will produce until we analyze the sample. And last observation, even though our estimator p-hat isn't always equal to p, we're never more than 25 percentage points away from p. In fact, the standard deviation for this distribution is 16.4%. Remember that this standard deviation talks about the average distance from the center of the distribution. And you're going to confirm the standard deviation in the group activity that goes with this section. And last question on this page, how does our approximated sampling distribution compare to the exact sampling distribution for this experiment? Well, remember that the approximated one, and you can flip back a page to double check this, but the approximated one, got 0%, 25%, pushing this in here, 50%. All of these had a probability of 0.33%. That was from our simulation. Right, so we do have some similarities. We go back up and compare that to the exact one, which is up here. What we can see is that they're both symmetrical. So they're similar in that regard. They both have a center at 25%. It's another similarity. But if you look, the exact distribution is unimodal. It has a peak in the middle. And the approximated one here is uniform. It doesn't have that peak in the middle that the exact one does. So what we'll find is that we'll need more samples or more repetitions to get our approximated sampling distribution to look more or get closer to the exact sampling distribution. Okay, number 9. When measuring the quality of a survey, we'll be interested in evaluating the estimation or sampling method used, not in a single estimate from a single sample. So there are 2 questions that we need to address. First question, are the results from a particular sampling method accurate? In other words, are the estimates centered at p? This can be measured in terms of the bias. A biased method will produce results that are not centered at p. So what does a sampling distribution look like when the results come from an unbiased sampling method? And what does it look like if it's from a biased sampling method? So we'll give an example here for unbiased, and we'll do biased on this side. And again, if you'd like, press pause, try this out first, and then press play when you're ready. Right, so if something is unbiased, and by the way, we're going to continue to assume that p is 25%. We'll keep thinking about that cat and dog population. And so if sampling method is unbiased, you're going to find that most of your results are very close to 25%. In fact, they're centered at that value. Right, so we measure bias. In this case, we would say the bias is 0 by looking at where the center of the distribution is in regards to the p, the population proportion. So if we subtract those, we'll find that this gives us a bias of 0. There's no bias in this sampling method. So no bias means you have an unbiased sampling method. Bias, on the other hand, and again, keep in mind we're still thinking about that population of 25% cat people. If we have a bias sampling method, we might find that our sample results aren't centered at the population proportion. Okay, so in this case, we see that our bias is not 0. Our measure doesn't give us 0. So if we look at where the center is in regards to P, it's like our center is right around 5%, which is 0.05, minus where the center should be. We get an answer that's not 0. We get an answer that's negative 0.2 in this case. Okay, so our second question, question number 2, are the results from a particular sampling method precise? In other words, are all of the estimates similar in size? So again, we're going to continue to assume that P is 25%. Keep thinking about that cat and dog population. All right, so what does a sampling distribution look like when the results are precise? We'll do precise here. And how about if they're not precise? And so if they're precise, that means they're very compact and they have a lot of consistency. So they're going to be very close together. All your sample results are very similar in size. So now you get something that looks like this. If they're not precise, you're going to see that there's not a lot of consistency here. You get a lot of different possibilities. In fact, you might find that they're not even limited to just 50%. Maybe there's more values close higher above than that. And keeping in mind that our population only had, 2 cat people out of 8. I suppose we have to adjust that a little bit, but you get the idea. Precise means there's a lot of consistency, very consistent results, not a lot of spread. Not precise means that they're not consistent, or they have a lot of spread. So taken together, bias and standard error are used to quantify the uncertainty in our inferences. So let's return to approximated sampling distribution in number 7. So the question, do you think our sampling method was accurate, which means that it's unbiased? You can say yes. The center was equal to 25%. So if we do the center minus P, we get 0 or 0%. So that's an unbiased sampling method. And then the second question, do you think your sampling method was precise? You can say somewhat. We don't really have a measure yet to tell us if that's definitely a yes or no. But we can say the standard deviation was 16.4%. Remember, that was given to us. Okay. So no, we can also say that again, it's somewhat precise. It was probably precise because p-hats weren't more than 25 percentage points from P. So one of the questions we're really interested in later is how can we increase the precision of the sampling method? All right, so some key features of a sampling distribution. One is the probability distribution for a statistic. It shows all of the possible values of the statistic on the horizontal axes. It gives us the probability of each possible statistic. This tells us how often we can expect to see particular values of our estimator. It gives us important characteristics of the estimator, such as bias and precision. Bias is measured using the center of the sampling distribution. It's the distance between the center and the population value P. Precision is reflected in the spread of the sampling distribution and is measured by the standard deviation of the sampling distribution. Standard deviation of a sampling distribution is called the standard error, sometimes abbreviated SE, and it measures how much our estimator typically varies from sample to sample, or how far estimators typically are from the mean, P. And the smaller the standard error, the more precise the estimator. And these sampling distributions are also used for making inferences about a population. All right, number 11, how do we find the bias and the standard error for the sampling distribution for p-hat? Well, one way is to run a simulation, which you'll do in the group activity that goes with this section. A second way is mathematically without running a simulation. And we can do this if the following conditions are met. So 1, the sample has to be randomly selected from the population of interest, with or without replacement. 2, the sampling is without, if the sampling method is without replacement, then the population needs to be much larger than the sample size. At least 10 times bigger is a good rule of thumb. So if these two conditions are met, then we know the following is going to be true. The bias of p hat is 0. This tells us that the mean of our distribution, and mean or center of our distribution is going to be p. And it also tells us that the standard error, SE, can be calculated with the following. So we take the square root of the population proportion times 1 minus the population proportion and divide that by the sample size. And keep in mind that p has to be in decimal form or fraction form, but it cannot be in percent form when you use this calculation. So you can keep in mind standard error is the name of the standard deviation of our sampling distribution. Okay, number 12, in a real-world application, keep in mind that we usually only take one sample from a population and calculate one p-hat, one sample proportion. Keep in mind that bias and precision are both measures of what would happen if we could repeat our survey many times. And also keep in mind that we won't know the value of p, so then how do we calculate the standard error? We can get a pretty good estimate of the standard error by using p-hat in place of p. So remember from the previous page that the standard error is calculated by doing p times 1 minus p over n. This should be pretty much the same. A good estimate, or standard error estimated standard error should be a pretty good estimate of the standard error. So they should be very close together in size. I mean, the only difference is we're using p-hat in here instead of p. And this is called the estimated standard error and is a useful approximation to the true standard error. So estimated, that's what that EST up here reminds us. All right, so let's try this out in number 13. So according to the Mars Company, packages of milk chocolate M&Ms contain 20% orange candies. So we're going to examine 100 random candies. So what value should we expect for our sample proportion of oranges or orange candies? We should expect that our p-hat is very close to 20%. Okay, give or take a little bit. That's what our simulation helps us see. That we know our p-hat doesn't have to equal the percentage of candies and orange candies in the population, but we know it's probably getting very close to that. Standard error can give us an idea of that give or take a little bit. So if we calculate this, remember we have p. P is 20% or 0.20. So I'm going to put it in decimal form to use this formula. I'm doing p times 1 minus p, and I'm going to divide that by the sample size of 100. I'm going to find that that's equal to 0.04. Okay. So we can take these two answers, and it tells us that we should expect about 20% oranges, give or take about 4%. Okay, so last questions in this section. Number 14, how small should the standard error be for a survey to be considered good? So the answer is small enough to be useful. So we're going to consider the following two examples to illustrate this. So let's say an election poll of 1,000 registered voters found that 49% favored the incumbent candidate. So we're going to calculate the estimated standard error. Just note that all we have is a p-hat because that's the result of the survey. We don't have the actual population proportion. So the estimated standard error is equal to p-hat, again I got to put that in decimal form, times 1 minus p-hat over our sample size of 1,000. And that's roughly, so I'm going to round this a little bit, 0.0158. Okay. Or if you want to put that in percent form, about 1.581%. Right, so a counterexample before we get back to the question of whether that's going to be helpful or not. In this case, it's another election poll of 1,000 registered voters, but they found that they had 59%, so this is their p-hat, that favored the incumbent candidate. So again, we're going to calculate the estimated standard error. Again, we need to put that in decimal form for this calculation. And this gives us an estimated standard error of 0.01555, or about 1.555%. At some point, you should press pause and just double check these calculations. And so the question is, in which case is the estimated standard error going to be more helpful? Well, note that in the first one up here, that we would expect, about 49% of the population is probably also going to favor the candidate, give or take about 1.5 percentage points or 1.6 percentage points. So in this case, the standard error is not really big enough to identify a clear leader, because that means that if we could go up or down about this much, then we would not really be sure if a majority favored the incumbent or not. Right? Versus in the second example, here, we had 59% that favored the incumbent, give or take about 1.5 percentage points. That means that we know, or we're pretty confident, that a majority of these people, or majority of the population, probably favor the incumbent, assuming that their poll reached out to a representative sample. So again, in this case, it's probably a little bit more helpful to us than it is in the first case. So again, assuming there are two candidates, the second estimated standard error is more helpful because it helps us better predict the outcome of the election. We're fairly certain or fairly confident that 59% will vote for the incumbent, give or take about 1.6%. That gives us an answer of more than 50%, again, a majority. But in the first one, again, we expected about 49% to vote for the incumbent, again, give or take a little bit, about 1.6%. But that leaves us with the question, is that going to be more than half or less than half that favor the incumbent?